Uh, Hello everyone. Welcome to today's Math Club talk. Today's speaker is Shahbaz Ahmed Khan. He's a BMath second year student and his interest lies in group theory, representation theory, and combinatorics. Today's topic is conjugacy classes and irreducible representations of a group. And if anyone has any doubts at any time, you can just type it in the chat. I will convey it to the speaker. Over to you, Shahbaz.
Hi, can you hear me?
Yes.
Yeah, so thank you, Harshal, and welcome everyone else. So this will be part one of two talks, and today I'll be laying down the foundation of everything I'll be needing in tomorrow's talk to prove the final result, which will be about conjugacy classes and irreducible representations. Unfortunately, I have to preface the talk by saying that due to time constraints, I won't be able to go into as much depth as I would have liked to. And there will be some results that I'll be stating without proof, mostly because those proofs can be talks of themselves. And one convention I'll follow is that anytime in the talk I use the Greek symbols phi, psi, or rho, there will be representations of a group G. G will always be finite. And the vector spaces will be over C, finite dimensional, and they'll always be denoted by V and W. Okay. So without further ado, let's begin by defining what I mean by representation. So a representation of a group G is a homomorphism phi from G to GLV for some vector space V. Here GLV, in case there are people who don't know linear algebra, you can think of it as matrices. So n cross n matrices with entries in C such that A is invertible. Of course, what I actually mean here is that this is a linear map between the vector space, but thinking about matrices is good enough for our purposes. I also define the degree of phi to be just the dimension of this vector space V, and I'll assume that V is never the zero vector space. Additionally, since the elements of GLV are themselves maps from V to V, so this matrix A can be thought of as a map A from V to V. And since I will be using this map in and of self, so to avoid having to write phi G V and make it look dirty, I'll underscore the G, right? Some trivial examples. So given a group G, I can always have the trivial representation. So this I will call the trivial representation. And then some specific cases, so I can have something of this form. So I take z mod 2z and I send it to -1 to the power of k. Here z mod nz is being taken to be, I'm not drawing bars or anything to denote that they're conjugacy classes, that's understood. And in general, you have this representation, but this is not an example we are very interested in for the purposes of this talk anyhow. We will be interested in an example about the group Sn, which we'll come to later. Now, for those of you that know linear algebra, you'll know that since my vector space V here is over Cn, or over C rather, what that means is V is vector space isomorphic to some Cn. That's understood. So whatever the dimension of V is, it's essentially isomorphic to C cross C n times. Right. Now, I would like to be able to speak of a representation phi and another representation psi from G to GL and C, as long as it's actually the same map, it's giving me the same map. But clearly, I've changed the vector space in a non-isomorphic sense. So technically, they're different, they're just isomorphic. But I would nonetheless like to be able to speak of them as one and the same. So if phi is a vector space, if V is a vector space and phi is a representation from G to GLB of degree n, then I fix a basis for V. Basis can be thought of as a set that gives me the entire vector space. And then there's the canonical isomorphism by taking coordinates. And I can then define a new representation, psi, by instead of mapping it to the abstract maps that are in GLV, by mapping it to the associated matrix when I take the coordinates. And that follows from this equation. But of course, a vector space does not have a unique basis. It can have more than one basis. And if B dash is another basis, then the coordinate isomorphism will also be different. And therefore, this will give me a different map. Intuitively, it should be clear that since the vector space in a abstract sense isn't really changing in terms of the algebra that it does, I would like to be able to consider them the same representation, at least in some sense. So akin to isomorphisms in group theory or linear algebra or ring theory, in representation theory, I define equivalence of representations. So I call two representations to be equivalent if there is a vector space isomorphism between the two vector spaces that they are on, such that this equation holds for all G. A trivial observation that can be made here is that since I'm assuming or rather enforcing V and W to be isomorphic, this does imply that dimension of V will be equal to the dimension of W, or in other words, the degree of phi will be the degree of psi. That doesn't require a lot of thought. So far I have a representation which is just a homomorphism. And now I have a notion of equivalence.
Will be dimension of W.
Yeah, sorry. Thank you. Yeah, so another example, all the previous examples were degree 1 representations. So if I have C square or C2 rather, then I can define this to be a matrix or this to be a representation and this to be a representation. So note that these matrices in and of themselves. So phi m itself is a map from C2 to C2. Right, and if I look at the matrix, I can give the map by multiplying by the column vector. And some of you may recognize this as the rotation matrix. And these are equivalent. So we can consider this matrix. By this matrix, I mean the matrix of this map T. And that will give me the equivalence. You need to calculate the inverse. I won't do that calculation, but this matrix will show you that these two are indeed equivalent. Now, this will be an example that I'll be very interested in the next talk, or at least briefly interested in. I'll be using it to prove a preliminary result. So if Sn is the symmetric group on n symbols, so Sn is the symmetric group. For ease of convenience, I will just write 1 to n instead of any old n symbols. I define the standard basis, or rather I define it on the standard basis by this equation. So note that as soon as I define a linear map on the matrix, I am given the entire map. Right? You must have seen this in group theory for the first years, that if you define a map on the elements that generate the group, you get the entire group out. And I can obtain the matrix for this representation by permuting the rows of the identity matrix according to sigma. So sigma is a permutation of 1 to n. For example, if I have phi from S3 to GL3C, then the matrix of something like phi 132 will be, so I start with the identity matrix. I'll just do this as I would while doing a problem. Then I permute the rows. So 1 goes to 3. And 3 goes to 2. 2 goes to 1. So this will be the matrix. and so on. This will be an example that gives us something interesting in the next talk. I won't be going into that for now. But yeah, so this is an example worth remembering. I'll be using this in my next talk. Now, everything in algebra, at least most things, they tend to break down. So groups break down by the structure theorem, modules break down by the structure theorem, prime numbers break down by the fundamental theorem, polynomials split into things that you can no longer split. And I'd like to have a similar notion for representations. So first I need a notion of invariance. So akin to polynomials no longer splitting further, I'll need something of that sort. So let phi be a representation and W be a subspace of the vector space V. So this is a this is what you would naturally expect it to be. It would be a subset of W that's a subset of V that's a vector space in and of itself. And I call it G invariant if for all G and all W in W, the map phi G never goes outside of W. So you can also write this as image of phi G when restricted to W lies in W. And I call a representation to be irreducible if there are no other G invariant subspaces, then the two obvious ones. So the zero vector space subspace and the entire vector space. There are a few other related notions, namely decomposable representations and also completely irreducible representations. But I won't be needing these explicitly, so I won't be going into them. There's a beautiful result called Marshall's theorem that I'd like to mention, which states that every representation of a finite group G is completely reducible. So that would be your analog to a fundamental theorem. That would be your analog to factorizing numbers. Right. Now, any degree 1 representation is always irreducible. This is trivially true since the vector space. Okay. So I should mention why my degree 1 representations are over C star and not GLC. That's because GLC would be 1 cross 1 matrices, so just complex numbers, which are invertible. That is everything in C but 0, so C star. If you want to, you can write it as an isomorphism and make this look like this, but obvious enough. Yeah, so any degree 1 representation is reducible since there is nothing that you can reduce. In order to reduce this, or for it to not be reducible, I would need a subspace of C star that isn't the entirety of C star or 0. But because it is a degree 1, dimension 1 vector space, it doesn't have any other subspaces. For the trivial group, a representation is reducible if and only if it is of degree 1. This should also be fairly straightforward. And a slightly non-trivial example is that if I define a representation like so on the generators, the representation is then irreducible. I'll give you a proof of this on the next slides, and that highlights a relationship between eigenvectors and irreducibility. And finally, the rotation matrix representation that we saw is also not irreducible. For instance, consider the span of I1. By this, I mean consider the vector space of this span. So I take any complex number, I multiply it to I1. This is then a subspace of C2. And as it turns out that this subspace is G invariant. Okay, so let's prove the third example. So rho is a representation from S3 to GL2C defined on the generators 1, 2 and 1, 2, 3 as rho of 1, 2 is this matrix and rho of 1, 2, 3 is this matrix. In order to prove this, we first realize that since the vector space I'm working with is C2, so here V is C2, the only non-trivial subspace that I can have is going to be of dimension 1. So this is the subspace other than 0 and C2 has dimension 1. And since the dimension is 1, it will be generated by some single vector. So I assume V is that vector. Then CV, which here denotes the span of V, gives me dimension 1 subspace. And I assume that this is S3 invariant. So I'm assuming the implication that I'm going to prove is false. And yeah, so I assume that there is a dimension 1 S3 invariant subspace of C2, and I consider sigma to be a permutation in S3. Then the value of rho sigma at V should be lambda V for some constant lambda. This is because I've assumed S3 invariance. So S3 invariant implies that they should be in the same vector space, on the same subspace, which means that this needs to be lambda V for some lambda constant. And this precisely means that V is an eigenvector for every matrix sigma rho, or every linear map sigma rho, however you want to think about it, where sigma is any element of S3. Specifically, these two matrices have a common eigenvector. But we can show that that is not the case. So we can find that sigma, or rather rho 1, 2 has eigenvalues 1 and minus 1, and that the eigenspaces are given by V1 and V minus 1, which are the spans of these two. Okay, they should be span of these two vectors, and that none of these work for rho 1, 2, 3. Fine. So I get that they don't have any common eigenvectors, which was something my assumption had previously implied. And therefore, my assumption was false, and they are irreducible. The representation is irreducible. This holds in general for any degree 2 representation. So a degree 2 representation phi would be irreducible if and only if there is no common eigenvector V to all phi g with G belonging to G. Also holds for degree 3 representations. Though the proof isn't as straightforward as the degree 2 case. In the degree 2 case, you can simply just trace along what I did as my example, and the proof follows. Right. Okay, so I want to prove one more property, which is that if phi is equivalent to an irreducible representation, then phi itself is reducible, which is something we will naturally like to be true, since equivalence is our analog to isomorphism. So we'd like representation theoretic properties to be preserved naturally. I don't give a proof of these because this will take some effort and some things that I've omitted thus far. But this is intuitive enough for everyone to not hate me for it. Yeah. Now I need one more notion about representations before we have any sort of structure to talk on in the next talk. And that's of unitary representations. So, yeah. So let V be an inner product space. By an inner product space, I mean V is a vector space. With what most people may be familiar as a dot product or scalar product. Defined on it. So if V is an inner product space, I call the representation phi to be unitary if phi G is unitary for all G belonging to G. What that means is that if I take the dot product on these, I can simply get rid of the map and just take the dot product on the vectors. And this holds for all V comma W will divide. Okay, this should be W there. Yeah. So in other words, phi is a map from G to UV, where UV denotes the set of unitary operators on V. Again, I know that part of the audience is from the first year, so they don't know much linear algebra, if at all. And maybe some of this isn't making a lot of sense. I'll do my best. Feel free to ask in case there's something that you don't understand, and I'll try to explain. Okay. Here's an interesting result. So, as previously, I identify the 1x1 matrix with the complex number Z. Then Z is unitary if and only if the conjugate of Z is Z inverse. That is, if and only if the modulus of Z is 1. So the unitary operators on C are just the unit, can be thought of as the unit circle in C. So a degree 1 unitary representation will just be a homomorphism from G to the circle T in complex numbers, radius 1 circle, obviously. And the first important, non-intuitive, non-trivial result is that every representation of a finite group G is equivalent to a unitary representation. This is something I will be using to ease my life when I'm proving certain things about characters in the next talk. Maybe in this talk, I don't remember. I think it's in the next talk, but yeah. Okay, so we prove this, and I start with the representation phi from G to GLB, and I assume that the dimension is n. So far, so good. I fix a basis for B, and I let T be the associated coordinate isomorphism. I define a new representation, as I did when I was motivating the definition of equivalence by this equation. And naturally, these are equivalent representations. I let this be the standard inner product on Cn. And I define a new inner product by this equation. Is this an inner product? Do you want me to check? Or is this fine? Okay, this should be fine. And with this inner product, we observe that the representation turns out to be unitary. So I want to go back and make another remark for first years. I suppose everyone else should be familiar with this. This sounds like a very bad representation definition on first glance, because you can ask me the question, is there always an inner product space or inner product on V? And the answer is no, in general. So for example, if V was over some finite field, there's a possibility it doesn't happen. But since I have assumed my vector spaces to be over C and to be finite dimensional, for us the answer is yes. And for us, it's not very difficult to come up with an inner product either, since my V is always going to be isomorphic to Cn. And then you can take the standard or obvious inner product that you may have seen in school. So for example, okay, never mind. Let's not waste time. I'm already halfway through the allotted time. Yeah, I'll try to keep this around 1 hour so that we have some time for questions. And depending on how much I actually end up covering, I'll maybe adjust the next talk to cover some more. Okay. Yeah, so I won't be needing this inner product again, but this is what's called the averaging trick. And you do need this to prove certain results, the same trick. And these proofs will be something I omit later on in the talk. Again, due to time constraints and lack of machinery to work with. Yeah. Now morphisms. So we have an analog to isomorphisms. Now I need something slightly weaker, an analog of homomorphisms. These are also called intertwiners or intertwining operators. So let phi and rho be two representations on two different vector spaces possibly. Morphism from phi to rho is defined to be a linear map T such that this equation holds. So T phi of G is rho G of T. You can think of this as composition or matrix multiplication, whichever you're more comfortable with. And this holds for all G belonging to G. Note that I cannot write this as T phi G T inverse is equal to rho G, since my T is just a linear map, and it's not necessary that it is a invertible linear map. If that were the case, then it would just be an equivalence. Right, I denote the set of all morphisms from phi to rho by this, which has a name that you will soon know if you don't already. And note that this is a subject of this, which is something I won't be needing, just a passing remark. In fact, it is not just a subset, it is a subspace of home v comma w, whatever that is. And it is also easy to observe that an equivalence is just an invertible morphism. So an isomorphism is just a bijective or otherwise invertible homomorphism. Similarly, an equivalence is just an invertible morphism. Okay. Then you have the result that seems to hold in every branch of algebra, that the kernel is something you would like it to be, and so is the image. So in our case, the kernel of a morphism is a G invariant subspace of V, and the image of a morphism is a G invariant subspace of W. This is again not very difficult to prove. So if V is in the kernel of T, and okay, G belongs to G, then T phi G of V is rho G T of V. So again, I had initially only written T phi G is equal to rho G T, but please don't forget that these are themselves maps from V to W or V to B or whatever the situation is. They are linear maps in and of themselves, so I can input values into them as well. That's what I do here. So this holds for all V, in particular my V, and V is in the kernel of T, so this is 0, and therefore this is 0. Hence, the kernel is a G invariant subspace. Similarly, for the image, you have rho G W, which is rho G T of V for some V. You use the defining property of a morphism, that is, you write rho G T as T phi G, and you get it in the image as well. And I don't prove this, I won't be needing this, but neat little result anyhow. Suppose this does tell you that you can do certain things, but I do not think I'll be needing them. Right. Now the first big result of representation theory, the first really important named result, that is Schur's lemma. And you may be used to seeing this in some other form. I'll get to that in a while. So if I have two irreducible representations of a group G, and I let T from homomorphism of G to, or rather T is a morphism between from phi to rho, then T is either invertible or T is 0. Now, this is immensely important because what I say here is that if I intertwine these two representations and they're both irreducible, then either they are equivalent or I've done something pointless, that is t is 0 and I don't get any info that I would like to have. And this cuts down the possibilities of how many morphisms are there by a fair bit, makes working with it fairly easier, as we'll see in the next slide. And the proof again is not very difficult, at least of this statement alone. This is not the form I'll be using Schur's lemma in most of the time. I will be proving two consequences of Schur's lemma, which are also sometimes just called Schur's lemma themselves. And those will be the statements that we end up using most of the time. So let phi be a representation, a V representation, and rho be a W representation, and let T be non-zero. So of course, if T is 0, then I'm trivially done. If T is non-zero, then by the previous proposition, the kernel of T is a G-invariant subspace of V. And that means that the kernel of T is V. Why is that? Because I am assuming phi and rho to be irreducible. And by irreducible, I mean that they only have two G-invariant subspaces, 0V, and that's it, and 0W in the case of rho. So if kernel of T is a G-invariant subspace of V, it is either 0 or it is V. Since the representation is not 0, or rather the morphism is not 0, this cannot be the case. So kernel of T must be the entire vector space, which, using a standard result that we see in linear algebra, means that T is injective. Similarly, the image of T is also a G-invariant surface of W, which implies that it is either 0 or the entirety of W. And once again, since T is not the 0 map, the entire image cannot be just 0. So the image must be the entire vector space W, which means that T is surjective. Therefore, T is bijective or invertible. Now, the form I shall use these statements in is this. If I have two,
Shahbaz,
yeah,
am I audible?
yeah. Is there a doubt?
Yeah. Shahbaz, the thing. So yeah. So it's given T is non-zero.
Yeah.
आवाज कट रही है क्या?
Oh, there should be 0 here. Yeah, I get what you're saying. Yeah.
Am I audible?
Yeah. You're audible.
Okay, so it's given T is non-zero. So shouldn't
the kernel should be 0. Yeah.
And
That's
not V.
Typing error. Yeah, my bad.
The kernel is V means everything is 0, right?
Yeah. Temporary loss of information. Yes. Yeah. Thanks for pointing it out. So the kernel is 0. Otherwise, the map is 0.
I think there is a lag. I'm sorry.
Okay, it's fine. Okay. So yeah, thanks for the correction. And yeah, so the form I'll be using Schur's lemma in is this. If I have two inequivalent representations, then there are no morphisms between them other than the 0 morphism. And if I have two equal representations, then all the morphisms are of the form lambda I, where I is the identity matrix of order n. And now you can see what I meant by when I said that Schur's lemma simplifies our handling of morphisms since there's not a lot of them. Okay, so the first statement is obvious. I don't think I need to mention anything. If T is invertible, then they are equivalent, which is not the case here. So T must be 0. Therefore, the first statement follows. For the second statement, I use a known result implicitly. Since our underlying field is C, T has an eigenvalue, which I call lambda. The reason behind this statement is that the underlying field is C, and so every polynomial is going to have at least one root. In particular, the characteristic polynomial is going to have at least one root, which is precisely what an eigenvalue is. So lambda I minus t cannot be invertible since I is a morphism itself. So is lambda I minus t, and so lambda I minus t must be 0. Fine. And this, I don't think I need to write this nonetheless. And this will be the form I shall use this in. If I get a chance to use it at all, since I have to, yeah. Okay. I wanted to mention some more results that follow from this, since, okay, are there any doubts so far before I proceed further? Okay. Yeah, so in case you're someone who's not naturally interested in web theory, it makes sense for you to not find this interesting since, okay, I'm defining things and I'm proving things about what I just defined. And there has to be some use of this in some other area of math. So it should help me answer some other problem that isn't in and of itself a representation theory problem. So to that extent, I give a few corollaries. Let G be abelian, then an irreducible representation of G has degree 1. Corollary 2 follows from corollary 1. Let G be abelian and phi be a degree n representation. Then there exists an invertible matrix T such that this matrix is diagonal for all G belonging to G. And I then prove a result in neural algebra, which is usually proven using lots of complicated nonsense or rather not very elegant looking things. And that is, let A be a matrix of finite order. By finite order, I mean there exists some n from to n such that an is the identity. Then A is diagonalizable. Moreover, if n is the order, then all the eigenvalues are actually the nth roots of unity. Okay. Now I take a break from representation theory, at least explicitly, and I switch over to character theory, which a lot of people do study without any representation theoretic context to it beforehand, but we won't. So for me, a character, I define it to be the trace of this matrix. So let phi be a representation from G to GLV. Then the character chi of phi is the map G to C is defined by setting chi phi of G to be the trace of this matrix. So, okay, I say matrix, but this is possible that this is a linear map, not the associated matrix. In that case, the trace is just defined to be the trace of the associated matrix. And okay, I mentioned that this is well defined since for any two square matrices A and B, we have the equality trace of AB is equal to trace of BA. The reason I needed this is that chi phi of GH would be trace of phi GH, which is trace of phi G phi H, which is trace of phi HG. No, what am I saying? Yeah, no, I don't think I needed this. Why did I mention this? Okay, never mind. And the character of an irreducible representation is called an irreducible character. And to avoid any complications in what I'll be saying, I just assume all representations to be GL and C. So trace makes immediate sense. Fine. Okay. If phi is a degree 1 representation, then chi phi is just the representation. This is obvious since the trace of phi G is the trace of some 1 cross 1 matrix, which is just a complex number. So the trace is the single entry of the matrix itself. So I won't distinguish between degree 1 representations and their characters. And I can say something like chi is a degree 1 representation. That's also fine. And let phi be a representation of G, then the value of the character at identity. So this is the identity of the group, is the degree of phi, or the dimension of the vector space V, which is again not very difficult to see since one will be mapped to the identity matrix, and the n cross n identity matrix will have trace n, and n is precisely the dimension of the vector space or the degree of the representation. Okay, now this may seem like an excessive constraint, that why can I do this? But the reason I can do this is if phi and rho are equivalent, then their characters are equal. And so given any representation G to GLV, if I want to talk about their characters, I can simply switch to the representation that I obtained by taking the coordinate isomorphism to Cn and talk about that representation. So to prove this, we consider phi and rho to be matrix representations and compute the characters directly, noting that there is a matrix T such that this happens for all G belonging to G. This is a straightforward proof. I define class functions to be functions that are constant on conjugacy classes. So finally, we are now somewhere in the realm of what the title of this talk was. So a function f from G to C is called a class function if fg is equal to f hg h inverse for all g comma h in G. In other words, it's constant on conjugacy classes of G. We denote the set of all class functions by Z and G. And this suggestive notation is because this ends up being the center of the group algebra LG, something I won't be defining or talking about any further in the talk. Though I will be using the standard dot product on the group algebra every now and then. Yeah, we'll see when we get to that. And characters are class functions. So chi phi is HGH inverse. Chi phi of HGH inverse is the trace of phi HGH inverse. Since phi is a homomorphism, I can write this down like so. And since, as I previously mentioned, trace of BA is trace of AB, I get this equality. And then these cancel out to give me identity. And identity multiplied by phi g is obviously just phi g. And trace of phi g is precisely the character of G. Okay. Now I mention some useful results without proof, mainly because we're already have like some 15 minutes left, and if I had tried to mention all the machinery that I'll be needing to prove some of these, I would need more than 2 talks. Okay, so a representation phi is reducible if and only if the dot product of the character with itself is 1. The dot product here is this thing. This will be the dot product in most places in the talk, though I will be sure to mention it everywhere. And we get finally a counting result, which is this. So let phi 1, phi 2, and phi s. So these aren't powers, these are just an index. Be a complete set of inequivalent, irreducible, and unitary representations of G. That sounds like a lot to enforce. Okay. So representations have a notion of equivalence in between them. And if I talk about the equivalence classes, I know that in every equivalence class, there is going to be one unitary representation at the very least, since every representation is equivalent to some unitary representation. So I pick those equivalence classes which are irreducible, and I pick the unitary representative of that equivalence class. So this makes sense to do. It's not something wildly limiting. Okay. And I said di to be the degree, this should be I here. and chi I to be the character of chi phi I, then the formula that the order of G is the sum of degree squared holds, and the set of the characters forms an orthogonal basis for the center of the group algebra, which is a result you need to prove some important and amazing results. But I won't be. Yeah, so let C be a conjugacy class. G, define the function delta C of G to be an indicator function. Then the set delta C forms a basis for ZLG. This dimension of ZLG is equal to the number of conjugacy classes of G. So combining this statement and this proposition, I can get fact 3, which is that the number of irreducible representations and the number of conjugacy classes of G are equal. Okay. Yeah, so I want to mention a few more results, again without proof, because again, proving them would make this a half course in representation theory, which it certainly isn't. And yeah, so these are called the orthogonality relations. These are, again, very useful, akin to Schur's lemma. And okay, so let G be a group. Suppose phi from G to U and C. So U and C is again unitary matrices of order n. And rho is a unitary matrix from G to U and C are inequivalent, irreducible unitary representations, which is again not a very strong assumption. Then these two weird looking things that we haven't seen before hold. So here phi ij isn't phi of ij. So I and j are group elements. By phi ij, what I mean here is phi ij is a map from G to C defined by so it is the ijth entry of the matrix of phi G. Okay. And do I need something else to explain this? Okay, no, I don't. And this is also not a result I'll be using explicitly because, again, I won't be proving a lot in this talk. I will be proving a fair few results in the next talk. So it's not like I'll be just stating things till eternity. But this holds. And this gives me two more useful, again, so similar to Schur's lemma, this leads to consequences that are more useful, or rather that look more useful. Okay. So I have the first orthogonal integrations. Let G be a group and let phi and rho be irreducible representations of G. Then if I multiply the characters, or rather I take the dot product of the characters, then it is 1 if they are equivalent and 0 otherwise. This is immediate, not immediate, but a straightforward corollary of Schur's orthogonality relations. So to prove this, I let the two representations be unitary. And I can do that since the character doesn't change if I take equivalence. And you do some dirty computation to conclude that this holds. Then by Schur's orthogonality results, it follows immediately. So if, okay, maybe I can handle the two cases. If they are equivalent, then we more or less end up in this situation. And I get 1 over n for every time that I is equal to k and j is equal to L. So phi I, phi right, phi I, phi j. This is going to be 1 over n when I and j are equal. So this summation is equal to 1 to n. Note that in this case m and n, so this m and n are equal, right? And j is equal to I, which is only going to be one term. And if they're not equivalent, then it's 0, and there's not much to be proved. And finally, I have the second orthogonal integrations, which is something I will be using a lot in the next talk. So let G be a finite group with irreducible characters chi1 to chi-s, and let C and C dash be conjugacy classes of G. Let G belong to C and H belong to the other conjugacy class. Then this summation evaluates like so. An important corollary of this, which is the last thing I mentioned, and I don't even explain what I mean by this, since I will be doing this in the next talk, is that the character table is an invertible matrix. So consider this to be a teaser for the next talk. This will be one of the things I prove on my way to the main result. And we're ended by 10 minutes, but I think that's fine since there's not much I wanted to say today. Yeah, okay. I think that's all. Are there any questions?
If there is any question, if anyone of you have any questions, you can just unmute yourself and ask.
Okay, so I suppose that will be all for today. And okay, so in the next talk, I should briefly mention what we'll be doing in the next talk. So in the next talk, I'll start by discussing conjugate representations. I'll discuss what the character table is. I'll discuss what I mean by real characters and real conjugacy classes. I will briefly mention what the direct sum of two representations is, mostly to motivate the character table. And then I will do the two main results, of which, suppose they're not very dazzling, they're not very cup is donut, donut is cup sort of mind bending, but they're very deep in a sense that the problem that they try to answer isn't one that a lot is known about. So the problem of counting the conjugacy classes of a group in general is a rather wide open problem, which if you can solve actually gives you the number of partitions, which is perhaps a more famous counting problem. And the result I'll be proving will give me a constraint on this number. So for a certain type of group. So if G is a finite group, mod G is odd, and S is the number of conjugacy classes, then this thing holds. Then S is congruent to mod G modulo 16. I hope I've written this wrong, otherwise that would be embarrassing. I've written this correctly here. And for those that want to see the proofs of all that I mentioned today, you can look up the reference book by Benjamin Steinberg. And you should be able to find all of these in the third and fourth chapters. Though again, for those that maybe don't know linear algebra, which looks like is a subset of the audience, maybe not the best idea to look at them yet. For example, the proof of Schur's lemma would have taken me some 30 minutes to develop. So yeah, they're lengthy proofs. I'm sorry I couldn't prove all of them. I would have liked to, but I only have 2 talks and I wanted to get to the main result, the thing that's most interesting to talk about. Okay, thank you.
All right. Thank you, Shahbaz, for today's talk. We'll meet tomorrow at 12. So yeah, bye everyone.